Alright, so recall that lower bound is something like a bottleneck for the problem, which means there is no way this problem can be solved in time better than the lower bound. Alright, so let's see what is going to be the lower bound for sorting. We have already seen few sorting algorithms. The first ones were insertion sort and selection sort. Both were taking quadratic time, that is n square, which was too much. Then we managed to bring it down to n log n, which was merge sort. And now the question is, can we improve this further? Like, can we make it, let's say, big O of n, that is linear, which is going to be amazing, or maybe n log n, right? Something like that. So in general, can we make this small O of n? Small O means like anything better than n log n, asymptotically. So this is a question we need to answer. And once we figure out an answer for this, the answer is going to be either yes or no, right? Yes or no. So yes means what? Yes means there exists some algorithm which can do better than n log n. So if there is an algorithm, we would like to find out that algorithm. So the research has to continue. But on the other hand, if it is no, in the sense like if there is no such algorithm exist, then we should be able to somehow give a reason why it is impossible to have such an algorithm. If we can prove that, then what it means is n log n is essentially optimal and we can stop worrying about sorting, because we have already figured out the best algorithm and we don't need to worry about it anymore, right? So that is the purpose of figuring out this thing called lower bound. And what we're going to see now is the answer for this question is no. In the sense, there is no way anybody can come up with an algorithm for sorting in a small O of n log n. And more specifically, it's going to be this is what I'm talking about is all about comparison based sorting. Okay, so in all of this sorting, insertion, selection, merge, the main operation we were doing was comparison, and that's what we're gonna see in this course, in this lecture. Essentially, we will prove that merge sort is optimal, right? That's what we're going to prove. In other words, we're going to prove that all sorting algorithms, so specifically all comparison based sorting algorithms, must perform this many steps, at least n log n steps, at least n log n comparison must perform. And what is asymptotic notation for at least? That is omega n log n, at least omega n log n comparisons. That is what we're gonna prove now. Okay, so this is the theorem. Alright, so to proceed this, first thing we need to see is, understanding what is going on in a comparison based algorithm slightly better, or maybe this is a different way of looking at comparison based algorithms. So let me just make a small example. Let's say I'm giving you a small array which has, let's say, 4 elements, 21, 42, 13 and 36. So these are 4 elements, and once you sort them, this is going to be 13. So this is after sorting. 13 should come here, 21 should come here, and 36 should be here, and 42 should be here. So one thing I want you to notice at this point is a comparison based algorithm doesn't really need to know what are these numbers, what is the absolute value of these elements. It doesn't need to know. All it needs to know is how are these values related, or just it needs to know if, for example, like let's take two numbers, and all it needs to know is which number is larger, whether it is this one or that one. It doesn't need to know about the actual value. So another way to see this is, suppose these are, let's say, these are n items, or n people, and what we need to do is perhaps we want to order these people in terms of their, in the ascending order of their, let's say, weights. So we don't really need to know what their exact weight is. All we need to have is a weighing balance where by which I can compare the weights of two people and figure out who has smaller weight, and accordingly I can sort them. So simply speaking, these absolute values are not important. Okay, so that is the first thing. And what exactly is happening in the sorting? So you are given an initial ordering of these items, and let's say the initial ordering is 1, 2, 3, 4, the usual ordering. And what we have done now is the first element, that is 21st, you have moved to position 2. So this is the new array. The first element you have moved to position 2. The second guy you have moved to position 4. The third guy you have moved to position 1. And the fourth guy you have moved to position 3. So in some sense, you are given like numbers, right? You are given numbers 1, 2, 3, 4. And what you have just managed to come up with is a permutation of these numbers. And that permutation I'm going to write like this. 1 has moved to position number 2, and 2 has moved to 4. 3 has moved to 1, and 4 has moved to 3. And if you look here, this is actually a permutation of numbers from 1 to n, which means the comparison based sorting algorithm is gonna give you an output which is nothing but a permutation among n factorial different permutations possible. That is output, right? The input is going to be an array of some numbers, like these kind of numbers whose absolute values are not important, and the algorithm is going to do a bunch of comparisons between these numbers, and at the end of the day what it is going to produce is this, right? A permutation of numbers from 1 to n. Because if I know this permutation, it is easy for me to construct this sorted array in linear time. So the only question is, how is this algorithm come up with this permutation? So this is the output. Basically, instead of viewing this as the output, I can view this as the output, because if I know this, I can easily construct this in linear time, because I can scan this one and this one together and I can construct this one easily, right? So this is a different way of viewing sorting, or different way of viewing comparison based sorting, right? So comparison based sorting is what? Input is a set of n numbers, and what is going to the output? Output is a permutation. Is one permutation among n factorial different permutations possible, right? Good. So I want you to keep this in mind. Input, set of n numbers. The algorithm is going to do a bunch of comparisons, and at the end it is going to produce a permutation. Let's continue. So what we have is an algorithm for comparison based sorting with input is an array of or a set of n numbers. Basically input is n numbers, right? N numbers or n items, whatever. Now the algorithm is going to do a bunch of steps. I'm going to produce an output, and using the way we have seen before, the output is nothing but a permutation. Is a permutation of numbers from 1 to n. A specific permutation which is dependent on the specific instance of the input, maybe an array A. So that's what we can say about any algorithm for sorting, any algorithm for comparison based sorting. And what is going to happen internally, we don't know, right? What is going to happen? I mean, what are the exact steps this algorithm is going to do? We have no clue, right? I mean, basically, without assuming anything, we should be able to say that this algorithm must take that many steps, right? So, having said that, one thing we can say is this: an algorithm is essentially what? It's a bunch of decisions, right? So the basic operation is comparison. So the algorithm might compare two numbers, then the comparison is going to give you, comparison is going to give you an output. Basically, there are only two possible outputs or outcomes for a comparison, right? You have two numbers, you compare them, and you have to figure out either this one should go first or this one should go first. So compare, you have one of the two possible outcomes, and based on that outcome, the algorithm will take some decision. We don't know what it is going to do, but it will do something. Maybe rearrange some numbers, or maybe move something here and there, etc. We don't know, but it's going to do something. Then after it does some operations, it will ask for another comparison, right? It will ask for another comparison, and based on the outcome of that comparison, it will do something else. Then it might ask for more comparisons and more steps, etc., etc. So this is what is going to happen in the case of any algorithms. So essentially, you compare two numbers. Which two numbers? I don't know. It will compare. Then the comparison is going to give comparison is going to have two possible outcomes, and based on those outcomes, it will again do some bunch of steps, right? It will again do a bunch of operations, maybe moving things around. Then again it will ask for another comparison, etc., 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 until it reaches one of the n factorial different permutations, which correctly represents the sorted order of these numbers. So this much we can say. So whatever I have said now, we can kind of represent in the form of a decision tree. Decision tree. So we can kind of represent this in the form of a decision tree, which exactly means this. At first, it's going to do a comparison. So each of this is going to be a tree, a binary tree, with each of the internal node represents a comparison. So this is, let's say this is a first comparison. So it has two possible outcomes, and if it is on this side, then it will do something, and maybe it will ask for more comparisons. Similarly on this side, again more comparisons. Maybe this side will need more comparisons. This side will need more comparisons. And maybe if I do 3 comparisons here, I might figure out that okay, the array is already sorted, right? So let's assume this is the decision tree corresponding to our algorithm. I mean, corresponding to that algorithm which we are talking about, right? So this is a tree. It will take decisions and keep on going. It will keep on going down, and it will stop growing once we reach a node, specifically a leaf node, which actually correspond to one of the permutation, right? So these leaf nodes are like the answers, right? These leaf nodes are like the answers. The internal nodes represent comparisons, and the leaves represents one of the final outcome. So let's see what is happening in a tree like this. For a specific instance of the problem, it will do a comparison in the beginning, right? It will do a comparison in the beginning, and perhaps this comparison will tell you that the output is here. I mean, this comparison will ask you to go here. Then you might end up in doing more comparison, and it will ask you to go here. So this is again a leaf, right? And at this point, the next comparison might take you here. That means in just 4 comparisons, we were able to reach a leaf node which correspond to a solution, and we are done, right? Which means for some instance of the problem, we just need 4 comparisons and we will get the sorted output. On the other hand, for some other input, so some other instance of the input, after this comparison, the algorithm will take you here. The next comparison might take you here. The next comparison might take you here. The next comparison might take you here, and you will end up somewhere here. So in this case, you can see that the total number of comparisons you need to do is 1, 2, 3, 4, 5, 6. Previously it was 4, now it is 6. Right? Good. So what you can see is these leaves are nothing but the different solutions possible, or what I can say is solutions space, and the paths or the length of this path. Length of a path is nothing but the number of nodes, represents the number of comparisons needed to reach a solution, right? For a first solution, this is a number of comparisons you need to perform. For this solution, this is a number of comparisons you need to perform. So what is going to be the number of comparisons you need in the worst case? The number of comparisons you need in the worst case is nothing but the length of the longest path, which is also known as the height of the tree, and I'm going to use h to represent the height of the tree. All right, and let me use n, capital N, to represent the number of leaves. Okay, so number of leaf in the decision tree is, let's say, the number of leaves in the decision tree, I'm going to use capital N to represent that, is nothing but n factorial, right? The number of leaves in this tree is n factorial. Now, this tree, how this tree looks like, it depends on the specific algorithm, right? For one algorithm, the tree might look like this. For another algorithm, see here you see, this is not really a balanced binary tree. It's going to be a binary tree always, but it's not really well balanced, right? So you have like, some nodes internally which has one leaf again growing further, but one leaf is, dead at this point, etc., etc. So this could be the tree corresponding to one algorithm. Maybe another algorithm might have the tree which is like very nice, like, like well balanced tree, right? This could be the tree corresponding to another algorithm. But again, the number of leaves at the end is going to be n factorial. You can have another tree which looks like this at the root. Right? So again, this is going to be the height and the number of leaves is going to be n. What I kind of need to figure out is what is going to be the lower bound for n. For example, in this case, this is a well-balanced tree. This is a well-balanced tree where the number of leaves in the first level is 1. The number of leaves, the number of nodes in the first level is 1. Here it is 2, 4, 8, 16, etc. That is how it is going. Which means at the last level for this tree, h is going to be, at the last level the number of leaves is going to be n factorial, which is nothing but 2 raised to h, right? In this case, sorry, this is n factorial. In this case, what you see is the number of leaves is equal to the height of the tree, right? Or roughly equal to the height of the tree. So what can happen is h is equal to n factorial. H is equal to n factorial. On the other hand, for this tree, what you can see is, see, it has a height h, and it is not really a fully balanced tree like this. So that means the number of leaves is going to be smaller. Sorry, that means the number of leaves is going to be smaller than 2 to the h. Now, if you look at all of these things together, what you can say about any tree, is that the number of leaves n factorial is bounded by less than or equal to 2 to the h. Right? In this case, this was equal. In this case, h is equal to n factorial, right? In this case, h is equal to n factorial, which is clearly, n factorial is less than 2 to the h. And this case also, n factorial is less than, or the number of leaves is less than 2 to the h. So I can say this for any decision tree corresponding to a comparison based sorting algorithm. So that means h, what I can say is h is going to be more than log of n factorial. Always h is going to be more than log of n factorial. Now the last question remaining is, what is n factorial? Is there a nice way to represent n factorial, which is going to be like this? n factorial is nothing but n into n minus 1 into n minus 2, etc. 3 times 2 times 1. All right. So one thing I can say is, in this case, n factorial, if I replace, there are n numbers here, and if I replace each number with n, right, if I replace each number with n, what I can say is this inequality will become less than or equal to, and this become n to the n. It's n factorial is less than n raised to n, or in other words, log of n factorial is going to be less than n log n. It is less than n log n, right? That's not going to be useful to get a lower bound for x. Now let's see what else we can do. N factorial again. What I'm going to do is this. There are going to be n numbers here. There are going to be n numbers here. And I'm going to just take only the first n over 2 numbers. The first n over 2 numbers are going to be more than n over 2. The first n over numbers are going to be numbers larger than n over 2. So what I can do now is, if I pick only the first n over 2 numbers and replace each of them with n over 2, that is a number smaller than itself, what I can say is this is greater than or equal to n over 2 raised to n over 2, which means log of n factorial is greater than or equal to n over 2 times log n over 2, which is nothing but log n minus 1. Log n minus 1. So you can maybe ignore this 1. So that means log of n factorial is between n log n and n over 2 log n. Other words, log of n factorial is roughly a constant time, some constant, I don't know, some constant times n log n, which means this is greater than or equal to, and the asymptotic notation we have for greater than or equal to is omega. So this is omega n log n. So h is omega of n log n. This is n, and h is the number of comparisons in the worst case needed for any algorithm, right? So in conclusion, what we have proved is any comparison based sorting algorithm must perform this many comparisons. And if you assume each comparison is going to cost you at least 1 unit of time, this is a lower bound for the time complexity. Good. So I think this is the first lower bound result in this course. So one small exercise I can ask you at this point is, can we prove a lower bound, or can we prove that binary search is the optimal way to figure out, or optimal way to search for a number in a sorted array? Right? You are given a sorted array, and I will ask you, is this number there in this array? Right? And we know that binary search can do this in log n time. Can we prove that log n is the best, or log n is optimal? In other words, there is no other algorithm, something different than binary search, which can do this in time better than log n. And using something very similar like this, you can prove that binary search is essentially optimal. The idea is very simple. Again, you can have a view like this, like a decision tree view of the whole algorithm, of the whole unknown algorithm, and which is going to have how many leaves. In the case of a binary search, the input is an array and the output is a specific number or a specific position in that array, right? So the number of different outcomes is n, right? The position is like something between 1 and n. So the tree is going to have n leaves. Then you can write something like this: the height must be at least log n, and yeah, and that's how we get h is equal to omega of log n. Yeah, so that will give you a lower bound for searching, or that will give you a result which says binary search is essentially optimal.